a special case of this one so you'll believe it before we prove the more general case. Let's use p equals 7. Now notice this doesn't work for any prime less than 5 just because the discrete factorial is not defined. It would be negative. It maybe work for the gamma function or something like that, but it doesn't work for any prime less than 5, namely 3 and 2. Now notice for p equals 7 right here, you would get 6 times 3 factorial, all right, is congruent to -6, right? And again, that's when you substitute a 7 right here. But what you get right here is, what's this? This is 36 is congruent to -6. Mod 7. Now notice that this means the very same thing as 36 minus -6 is some multiple of 7. Okay, is equal to some multiple, and I'll just write 7k. All right, so you can see that it does work. All right, it does work for 7 at least, but that does not constitute a proof. Now let's take a look at the general case here. Now, an important thing to do here as far as proving the general case is, again, you start with Wilson's theorem, very well-known result from number theory that holds for all prime. And also notice that all through the processing here, we're going to use the fact that p is congruent to 0. And this is trivial in modular arithmetic. P is the same as 0 mod p, right? And it's trivial but powerful. Okay, and again, if those of you not familiar with this means the same thing as saying p minus 0 is a multiple of p. Well, it's trivially a multiple of p, okay? And so that's exactly what we do in this very first step right here. We take p to be 0, right? We take p to be 0. This just becomes -1, all right? And then so that's how you end up with this intermediate result, which is also a consequence of Wilson's theorem. P minus 2 factorial is congruent to 1 mod p. And again, it's rinse and repeat right here. We rewrite p minus 2 factorial as p minus 2 times p minus 3 quantity factorial. And again, you replace p with 0 just from right up here. And you see how the minus sign comes back. And we end up with 2 times p minus 3 factorial is congruent to -1. And again, we'll carry on in a similar fashion. This would be the same thing as 2 times p minus 3 times p minus 4 factorial is congruent to -1. Okay? But you see what happens right here, folks. You can see our result will follow because you can rewrite this. This piece right here would just be -6 times -6 times. See, you have the -6 right here, and then you still have times p minus 4 factorial. Is congruent to -1. Okay, and so right here you would have the minus signs cancel, and you would still have 6 times p minus 4 factorial. And y'all remember p is congruent to 0, right? So you can put p minus 1 right here, congruent to 1 minus p, excuse me. Okay. So again, folks, the first thing I did was just write it like this, and it follows from this statement. Multiply through by minus to get this statement. This became a +1, right? But then p is congruent to 0, so we just insert it because it makes for a nicer formula. Now you could leave it out if you wanted to. I mean, you could leave the p out if you felt like it. It just depends on what you prefer in the formula. Either one will yield the same result. I mean, will be an equivalent statement. So that's it. Okay, that's what we were trying to prove, is that 6 times p minus 4 quantity factorial is congruent to 1 minus p. And again, if you prefer to leave it as just 1, that's fine too. It's not a problem. Some people just like a formula with the presence of a variable. A little more makes it a little more concrete, but either way is fine. So anyway, this proves it. And a simpler case that we can check if you want, you can check it for 5. If you put 5 in there, you would get 6 times 1 is congruent to -4 mod 5, which it certainly is. This is for 5, folks. One way to see it is that 6 and -4 differ by a multiple of 5. They both leave a remainder of 1 also, which is something that you might consider useful. They both leave -4 and 6 leave a remainder of 1 upon division by 5. But anyway, this proves the result right here. So anyway, that's all. Thank you for viewing.